Hi, welcome to the fourth lecture of EEE 107, fourth lecture, part 1. In this lecture, we'll be talking about stochastic signals, a review of your random processes, stationarity, and ergodicity. Okay. So you learned about random processes from EEE 25, probability and statistics for engineers. Okay. So I hope you still remember that. Okay. So without further ado, let's move with the lecture. Just a review of the last lecture, we introduced to you Hilbert transform and quadrature filters. And the criteria for distortionless transmission looks like this. Basically, constant magnitude response and a negative linear phase response. And we also classified linear distortion and nonlinear distortion and how to fix them. Okay. So now, let's look at random signals. So what are random signals? Well, by its name, basically its value is random. Okay, so let's expand that. At any point in time, if you try to observe the signal at a fixed point in time, you'll get random values. Okay, so that sounds kind of weird, right? So, but basically, random signals are basically fluctuations. Okay, it could take any form, and we cannot really define it. Okay. So it can be thought of as random processes or basically a time-indexed collection of random variables. Okay. If you look at the random signal at a snapshot in time, you'll get random values. Okay. And if you try to plot the signal with respect to time, okay, as we try with all signals, it's also random. And this is actually the nature of communication signals in the first place. So if we try to transmit something, let's say an image, we can model it as a random combination of bits. Right? Or if you really want to try to characterize how an image is uh, transmitted from one point to another, if you try to characterize that bit by bit, you need to know the image first. But in reality, the communication system, even the communication system designer, does not know how the bits are arranged in the first place. And we can think of it as a random signal then. So it simplifies the analysis, right? What also is a random signal? Of course, the notorious signal that is present in any communication system. We've talked about this before. Noise is an example of a random signal. So it is important to know how a random signal behaves so we're able to analyze the noise that is impeding our transmission. Okay. So the problem is with random signals, as we know, if we talk about signals, we're talking about Fourier transform, energy, bandwidth, and so on and so forth. But since we don't really know how a random signal behaves, we cannot analyze its Fourier transform. Okay. Although these stochastic signals are unpredictable, we can analyze them using their statistical properties. So the statistical properties would be your mean, variance, autocorrelation, and so on and so forth. Let's define them. So first, the mean or the average. We have a time average versus an ensemble average. The time average is basically an average with time. Okay? For any sample function v of t, we define the time average as this. Okay? So basically, you just integrate the function. Okay? Now, the ensemble average, we take a snapshot in time and collect the values, the possible values of that signal, of that random signal from what we call an ensemble of signals. So it's, for example, here, at time tk, your signal can have these values randomly. Okay? And you know the distribution, right? So could have these different values. If we get the average of that, we're getting the ensemble average. Right? Time average, basically, you get your average with time, of course. That's the definition of time average. An ensemble average, you get the average of the random signal at a snapshot in time. What's the significance of these two averages? So we can say that a signal is ergodic based on their time and ensemble averages. A signal, a random signal, is ergodic if the ensemble average is equal to the time average. Okay? What is the implication of an ergodic signal? It means that the ensemble average is time independent. If we get the average of the signal here, or here, or here, if the signal is ergodic, then basically the statistical properties of the signal is the same. Or at least the mean of the signal is still the same, not the statistical properties. Okay. So the ensemble average can be obtained from the realization of one sample function only. So even if we try to get the time average only, we can only measure the signal in time, so we only observe this signal, we still get the same average if the signal is ergodic. Okay? And fortunately, for most real-world problems, at least for you, when you go through this course, we try to analyze random signals. Most of the signals are ergodic processes. Okay. Now let's define what we call the autocorrelation function. It's defined by getting the expectation of two snapshots in time of the random process, and then you multiply them. Right? And this is how you measure the relatedness of the two time instances T1 and T2 of a random process. Right? So what does the autocorrelation function tell us? You will see later. Okay? So just some special cases. If your times are equal, if you try to get the there you go. The autocorrelation of the random process at the same snapshot in time, you get the mean square value of the function, right, as a function of time, right here. You're trying to get the mean square value. Now, we can actually apply the autocorrelation in deterministic signals also. And for deterministic signals, well, instead of having an expectation, we have an integration. Right? And if tau here is equal to 0, that means you're getting a snapshot in time, right? And say there's no delay between your two signals. You actually get the uh, the energy of your deterministic signal. How do you solve for the energy again? Integral of negative infinity to positive infinity of the magnitude square of that signal. So by intuition then, since we're getting the magnitude square, the integral of that, we know that it's the energy, right? Then maybe the autocorrelation function generally defines the energy of a signal. Right? So let that be a food for thought. Okay. So now let's define the stationarity of a process. So another property of how we characterize a random process is it's by its stationarity. So stationarity pertains to the statistical invariance, to a shift of time in origin. Right. So this is the formal definition. So it's very very convoluted, very mathematical. It basically tells us that the statistical properties of your random process does not change with time. Right? That's it. That's what stationarity means. It means that even if, let me just clean this. So that means if we get the snapshot here, the snapshot here, here, and here, okay, we still get the same statistical properties, the same random variable here, the same random variable here, the same random variable here. The statistical properties at that point in time, at those points in time, are still the same. It doesn't matter. And that's what we call a stationary process. Right? And for many applications, this is a strict stationarity, the definition of a strict stationary process. Okay? But for many applications, we do not really require the process to be strictly stationary. The process in most real-world applications is stationary in the wide sense, or WSS. Right? And that means only the mean, right? The mean does not change with time, and the autocorrelation function only depends on the time difference of your snapshots. Right? And any signal, any random process that has or that satisfies these two conditions are called weak sense or wide sense stationary processes. If you have an ergodic process, it follows that it is wide sense stationary, but not the other way around. Okay. So a wide sense stationary process can be not ergodic. Okay. So most practical applications, random signals are wide sense stationary. Okay. And some properties of your wide sense stationary process, the autocorrelation at tau equal to 0 is basically the mean square. Right? And because of that, if we get the mean square of a signal, right, recall that it's the same as getting the integral squared of the signal. Excuse me. Then we can say that Rx of 0 is the power of a WSS process. Okay? So by using the autocorrelation function, we already get the power of a wide sense stationary process. So even if we don't know how the signal behaves, we can still characterize the power that it has. Okay? So the power of the signal is right here at tau is equal to 0. If this is your autocorrelation function. Your autocorrelation function also exhibits symmetry. Okay? So if we get the expectation of this function times this function, we get the autocorrelation. Now if we let some new t be equal to t plus tau, then this t prime right here, this will become t prime, this will become t prime minus tau, and this is the definition of Rx of negative tau. This means that your Rx of tau is even symmetric. Okay? So if you have WSS process right here, you just mirror that on the other side and you get the complete information about its autocorrelation. Finally, the maximum value of a wide sense stationary process is at Rx of 0. At tau is equal to 0, you get the maximum value. Okay? And that means that at tau is equal to 0, the signal is related to itself at maximum. Okay? And it kind of makes sense, right? You have a maximum at tau is equal to 0 since you're looking at the autocorrelation of a signal with itself at the same time. Okay? If you have a time difference between the two snapshots, then the signal may be related to itself, right? So after some time tau, also, your signal becomes uncorrelated with itself. So that means the current value of the signal did not depend on the previous value more than tau seconds ago. And that's how you view autocorrelation of a signal. The proof of this is equal to this. As you can see here, if you take the square, the expectation of the square of the addition, see here? Okay. Since it's a square, then that's always greater than or equal to 0. We're getting the mean square of their addition. And if we expand that, we get these two equations right here. All right? And then we have this one is basically the autocorrelation at tau is equal to 0. Also this one, since it's just a time delayed version, okay? And we get this expression right here. So it doesn't matter if your tau is positive or negative. You can just let this be an absolute value. If we have an absolute value, it's always greater than 0. Then it turns out that this is actually the maximum value of your correlation or your autocorrelation function. Okay. So another property of your autocorrelation function, we call it the Wiener-Khinchin theorem. So basically, first we define the energy spectral density for energy signals and the power spectral density. Recall that the energy spectral density is equal to this, okay? And it's related to this one, okay? So your magnitude of your Fourier transform squared for an energy signal, right? This is your energy spectral density. And if it's a power signal, then it's a power spectral density. Right? This is for deterministic signals, since we can determine their Fourier transform. Okay? And we actually define them from the magnitude square of the energy spectral of the original signal. This magnitude square can also be defined, as we have seen earlier, can also be defined using the autocorrelation function. So maybe if we look at it generally, the autocorrelation function actually defines the spectral density, energy or power, depending on the type of signal, of your random signal. And it shows us how energy or power is spread over or distributed over the frequency domain. Okay? So it could have a continuous function like this. It could have more power in this frequency here compared to the frequency here, and so on and so forth. And it's measured in, depending if it's an energy signal, then it's joules per hertz. If it's a power signal, then it's watts per hertz. Okay? And this is your Wiener-Khinchin theorem. If we apply it to random signals, since we can't define their function, then if we get the Fourier transform of Rx of tau, okay, since based on this relationship of your energy signal and your power signal, and this is the same as our autocorrelation function, if we get the Fourier transform of that, we actually get the spectral density of your random signal. So even if the random signal, we cannot really define it based on conventional knowledge of signals, right? Even if we can't define them, we can still characterize their bandwidth, we can still characterize their power, or energy, and so on and so forth, and we can still include them in the analysis of our communication systems. Okay, and this is an important mathematical formulation for random signals. Okay, because now we know that we can filter out random signals based on their power spectral density. Okay, or if we can determine their power and get the signal to noise ratio based on our transmitted signal, and so on and so forth. Okay, we can now predict how a random signal behaves based on their autocorrelation alone. Okay, and this is very important for communication systems. Okay? So let's expand then the definition. what if we have multiple random signals? The autocorrelation can be extended based on that using what we call the cross correlation function. Right? And this is how we can define the similarity between two random signals. Okay. Similarly, we can define what we call the covariance between v of t and w of t, okay, as a function of some time t1 and t2. Okay. And that is defined this way, right here. If v of t and w of t are both wide and stationary, then your cross correlation function is a function of a time difference only. Okay? And that, okay, those conditions, then your v of t and w of t are jointly wide and stationary. Okay? Can also define the independence, uncorrelatedness, and orthogonality. Two random signals are independent if their joint probability distribution functions can just be split into two factors. Okay, something like this. Two random signals are uncorrelated if their covariance function is 0. So that would mean that the expected value of v of t times w of t, you can just split the expectations right here. And two random signals are orthogonal if their cross correlation function is 0. Okay? And this will be important when we're analyzing multitudes of random signals that will impede in transmission. Okay? So for example, just a demo from MATLAB. Again, we'll talk about this during the live lecture. And I'll upload the simulation file if you'll miss it. So you can try to play it for yourselves. Okay? An earthquake data is, well, this is the given. And that's the end of this lecture. Okay? So there you go. If you have any questions, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.